No? Okay, so we have finished the plenary talks session. So now we are going to start with the speaker sessions with oral presentations. And I will introduce Ravi Kiran Kaipa from Northumbria University in the UK to deliver the talk on understanding the effect of chemical reactions on the surface grain structures, tube failures in economizers. So please proceed with sharing the screen and
Well, hello.
yeah.
Can you hear me?
Yes.
Yeah. Uh, Good morning and good afternoon, good evening, whatever it is to everyone. So, yeah, first of all, I'd like to thank the organizers for giving me the opportunity to present my current study of, research. It is still underway, so I could only share small details of it, like possibly very small details of it. Yeah.
Okay.
So yeah, the current topic that I'm going to talk about is understanding the effect of chemical reactions on the grain structures of materials, which is like connected to the tube failures and economizers. So, okay, what are grain structures? Well, is many get confused that it is just the atomic structures that we are going to study about, but these are different from the basic atomic structures, because atomic structures generally constitute like create the material that we get after getting it out of mining. And the grain structures are those which tells us about the features of that particular material the uh, with the you know com the chemical composition that it has got. So I'm going to go a little bit basic in the beginning, so that we could understand why these grain structures are important. Then we could talk about how is it affecting you know the economizers, which are highly used in the thermal power plants. Okay, so yeah, so the grain structures are generally differentiated into three types, which are like single crystal structures, polycrystalline, and amorphous. So yeah, single crystal, these are the type of crystals which only have one crystal, which is like only one kind of chem, material which constitutes throughout the metal structure. And these are generally, as you can see in this image, are very uniform in composition, and this is the only element, or the composition that is present throughout the surface of the surface of the material, which we'll talk about in the coming slides. Uh, you know, Secondly, the amorphous materials, as you can see it from the image over here, these are randomized version of single crystals, basically with very random atomic arrangement throughout the grain structure. And this can be mostly single crystals, because these are the kind of materials which are which are like semi-solids. And thirdly, it is polycrystalline structures, which is generally equal to single crystal structure, but with more elements added to it. So as we can see it from the image over here, it has got different what do you call element compositions, which can be divided as different greens over here. with different orientations of its unit cells, which is quite different from the single structure, because yeah, in single crystal structure it is all the same, all the unit cells are in the same orientation, but in polycrystalline it is different because of different element compositions in it. These polycrystalline structures are mostly used in all the engineering applications. Yeah. Excuse me. Coming to the material properties that we can obtain from the grain structures. Um, Firstly, these grain structures, or we can also call them as microstructures, these give out the information about a particular metal or material, if they are ductile or brittle or strengthened or etc. So these can be differentiated with the following classification. Like, we can check it with the help of grain size, we can check it with the help of phases present in it, distribution of phases, and yeah, elongated structures, which we can actually see in these images over here. The grain structure, the grain size, generally in any of the metal that is produced, the grain sizes will generally be uniform throughout the structure until and unless it is uh, you know manufactured according to the requirements of the client, or some client, or based on the application for which it is being used. So that is the grain size. And the phases, as I told you, phases are the the orientation of combination of unit cells that are present in a particular grain structure. So excuse me, in here we can observe that these unit cells, these are in different orientations for every individual grain, which indicates what kind of compound we can find in these grain structures. Like for example, if we are talking about ferrite or perlite that will be present in these grain structures, ferrites will have different kind of unit cell orientation, and perlites have different. So yeah, these are phases present, and the distribution of it. Yeah, distribution of it, because based, as I told earlier, based on the requirement, or based on its manufacturability, these grain structures tend to be variating. So because of which it is important to understand how these phases are distributed among the grains, in order to understand what is the property of that particular metal or material, whether it is ductile, whether it is hard, whether it is uh, you know resistant to like it is used for high temperature materials, high temperature applications, etc. So finally, the elongated structures. These elongated structures are basically the elongated version of what we spoke about the grain size. Uh, because as grain sizes are increased, uh, different the material properties tend to change according to the change in the grain size, which we will discuss going further into the analysis of how it is how we can observe these things in the uh, tube metal failures and the economizers. Excuse me. So these are the alloy elements that are basically found in all the boiler applications and its accessories. Economizer tends to be one of the accessory of thermal power plant boiler. So every element that is being used in the uh, that is being used in the sorry that is being used in the manufacturing of the tubes of that economizer are present over here, which indicates each element indicates its function, like how it is going to help the component that we are going to utilize for real life purposes. Like for carbon, it is used for increasing the solid solution strength and hardness. Manganese for like it counteracts brittleness caused by sulfur. And yeah, sulfur is generally one element which is considered impure, but still it is found in it is used in machining these particular components, because it is very helpful in improving the machinability. Silicon, which removes oxygen, because oxygen pitting is one such cause which causes tube failures in these power plant components. So silicon is used for that, for removing the oxygen from these steel carbon steel, or the steel applied for these components. And also it helps in decarburizing the the metal. And yeah, coming to the thermal power plants, these are the basic kind of power plants which we can find right now. Okay, uh, if we don't go into the future, these are the major kind of power plants right now, which works on a simple principle of heating the water and using that steam to run the turbine. And of these, coal power plants are highly found throughout the world. Mostly when it comes to India, coal thermal power plants are like the major power producing type of power plants that are that are currently in use. So yeah, so when we are talking about these power plants, excuse me, the main components of it consisting of boiler, superheater, economizer, because these are the main steam producing elements that are found in the thermal power plant. And of these, we are going to talk about the economizers. Economizers are generally used for heat treating, preheating the water which is going to flow into the boilers from the flue gases that are going to exit the boilers after converting the boiler water into steam. So before going out into the environment through chimneys, these flue gases are utilized. These heated flue gases are utilized to preheat the water in order to increase the efficiency of the boiler by reducing the amount of fuel that is being consumed to heat the boiler water. Yeah, coming to the tubes, tubes are generally the cylindrical structures which are used in transporting fluids, which can be liquids or gases. And yeah, it is very common that we find these tube applications almost everywhere around us. So we in here are going to talk about the tubes that are being used for high temperature applications, which generally deals with steam or water at boiler water at high temperatures, etc. So yes, what are tube failures? Well, coming to the power plant references, tube failures basically refers to damages that are caused to the tubes in the boilers or superheaters and economizers due to various causes which excuse me, which various causes which could reduce the efficiency of the plant and sometimes lead to total shutdown of the power plant, which is not good for the general uh, everyday life. Apart from reducing the efficiencies, these could sometimes be very dangerous because people working over there might get hurt dealing with while dealing with it. So analysis on the tube failures and power plants has been a topic of research for quite a long time, and we are going to discuss about it like in the coming slides. And yes, uh, uh, basically tube failures can be due to natural occurrences or due to human errors while operating the power plant. But in general, most of the time we could find human errors being the cause of these kind of catastrophes, which happen not so rarely, but quite frequently. And the major type of tube failures that we could find happening throughout many of the thermal power plants are short-term overheating tube failures, dissimilar metal welding, mechanical fatigue due to oxygen pitting, or caustic embrittlement. Well, this particular webinar is about chemical reactions. Mostly we will be discussing about oxygen pitting and caustic embrittlement. But I'll give a small brief about what are the other major types of tube failures that happen throughout. Well, short-term overheating is basically um, due to the ductile nature of the material that happens, which generally causes the tube to elongate and then explode in the form of fish mouth, as we can see in this picture over here. Which is caused mostly during boiler startups, because uh, failures in these boiler startups will uh, happen very rarely, but these happen due to extremely elevated temperatures from which could also result from the cooling systems not working properly. So the remedies for these kind of uh, uh, tube failures when they occur is generally to change the tube. That's all, because these are the mechanical failures that happens due to human errors. It is uh, well, it is basically very it will be good that if human errors are widely reduced, but yeah, uh, that is the other remedy which could the second one being the dissimilar metal welding. Yeah, to increase to reduce the cost, sometimes manufacturers use these kind of techniques. They sell these kind of products, which in general leads to catastrophes during operation of boilers. this is because sometimes these tubes have to go through a large amount of you know large amount of stresses that happen, because of which these generally occur. And it is better to avoid sometimes these kind of welding techniques that could result in these disasters. Well, coming to caustic attack. Caustic attack is generally due to the dissolved sodium carbonates that are present in the uh, boiler water, which generally flows into the boiler. And after heating it, it generally clogs the walls of the boilers. And sometimes these the steam also carries these elements throughout the tubes, which also clogs, creates a layer of um, you know sodium carbonate on the walls, which due to that there will be a difference, temperature difference created excuse me, temperature difference created between the tubes and the cooling systems while operating these kind of these boilers and superheaters and economizers. And yeah, when we are talking about the chemical reactions that are caused due to these caustic attacks, it is generally sodium carbonate producing sodium hydroxide while reacting with hydro water that is present in the boilers. And these sodium hydroxides, when they go and form a thin layer with the walls of the walls of the tube material, they react with these ferrites. And these ferrites in return are resultant in erosions. So generally in any power plant, while operating, it is necessary to calculate the amount of sodium nitrite and hydroxide ratio that is present in the water by using this formula. And the ratios with respect to pressures these are the general the amount of ratio of sodium carbonate or hydroxides that needs to be present in that needs to stay below the line according to these ratios over here with respect to the pressures that are being operated. So this is yeah, quite important to maintain the ratio of these compounds in the water with respect to the operations. Coming to the oxygen pitting. Well, oxygen pitting is generally the dissolved oxygen reacting with reacting with the walls of the boilers and others of its accessories. It is generally the localized kind of corrosion which leads to the creation of small holes, as we can see in these images, in the metals. These holes generally forms cracks, and sometimes would lead to boiler explosions and some care of. So yeah, tube failures and economizers, as we already spoke, it generally happens in general happens due to these mechanical failures. But sometimes it has been recorded that these tube failures occurs due to the chemical reactions like caustic attack or caustic embrittlement and oxygen pitting that occurs quite rare. But yeah, it is a point of interest for many researchers. So when we are talking about the study of grain structures, generally when preparing a grain structure for a grain sample for studying and uh, studying visually, it is very important that a small sample of the material must be collected and then polished in order to see the grain structures properly. And for that, apart from mechanical polishing, etching is one such process which uses chemical etchant, like in the case of steels that generally we use. It is the 98% of methanol and you know HNO3 2% that is being used, because these etchants help in showcasing the rough surfaces, as we can observe over here, uh, help in understanding the features of the grain structures which we can see through the microscope, or if the surface of the structure is quite plain, we could only see a bright image out of uh, out of the light that is reflected to view the grain structure of the particular image. So if so these reactions generally differentiate whether the following grain is a ferrite or a pearlite. So what is a ferrite? Ferrite is a property of ferrite is generally iron, and pearlite is a combination of iron and carbon, making it iron carbide. So each of it gives a different property to the following the metal which consists these kind of grain structures. Ferrite generally gives us the property of ductility of the metal, and iron carbide gives us the property of hardness and strength. So the ratio of both of these, like at what proportion ferrite is present, or at what proportion pearlite is present, these gives out the properties that going that gives us an understanding of how the metal behaves when coming to these kind of reactions and all. So yeah, when these reactions like caustic attack or oxygen pitting happens, the grain structures generally tend to form some spheroids, which we call it spheroidization. That is a process. Excuse me. Which is generally the impurity that that are caused after recrystallization of the grains. Every grain, after increasing the temperatures, increasing and decreasing the temperatures, they recrystallize themselves in order to adapt to the temperatures that are being applied to it. So the result of that are these periodizations, which uh, generally are the resultants of these oxygen pittings, or reactions of oxygen or sodium hydroxide on these materials. Because if we observe normal grain structure, it generally uh, gives out the properties of that particular metal, whether it is highly ductile, or due to the presence of pearlites, excuse me, highly hard or hard. So yeah, because of the decrement in the perlite, generally the tube failures happen due to increase in ductility, as we can observe in this image over here. And yeah, further we are currently studying the behaviors of the phases that I've, as I've mentioned earlier, which uh, if it either affects the affects the affects the metal in terms of its properties, or the change in its orientation would cause something. And we are also developing some image processing techniques to better understand these uh, you know these grain structures even effectively. So that's my presentation, and yeah, thank you. If anybody has any questions, I'm open for it.
Okay, so we have time so for some questions, 5 minutes. Any questions?
Well, I've taken some extra time, I guess.
Yes, Javier, I have a question for Ravi. One behavior that is observed in steam reforming furnaces, this is these are hundreds of pipes, and something that is not clear what's happening is these pipes, when the unit is shut down for maintenance, the pipes show they call them zebra pipes because it shows stripes patterns, but individual pipes, not, you cannot find in the furnace one area of the furnace that shows that, but suddenly a few pipes in different locations show that stripe pattern alongside. They don't not rupture, but they typically are replaced. But it's not clear if that's a thermal effect or is maybe some interaction with chemicals. If you would comment to that.
Well, I think generally what do we call these? The chemical reactions rarely occur in these pipes, because mostly these are very much in contact with the fire that burns, that produce, like, heats heats the boiler water. So it generally could be thermal stresses that are acting on it. On the other side, we can also say due to the impurities that are unfiltered while pumping the water into the boilers, these sometimes forms layers, some of a thin film or a layer of that particular compound, which could result in creating the temperature differences that could also result in that failures.
Okay, thank you.
Yeah, thank you.
Any other questions from the audience? I have one question. So you mentioned different types of tube failures, like welding, pressure, oxygen pitting, and so on. So, and you mentioned that they are quite frequent. So can you tell me, for example, what is the highest and the lowest failure rate for maybe some of the cases that you presented, or the frequency of failure?
Well, mostly, well, here in India, at least, most of the failures that are observed are due to, the dissimilar material welding. Because, sometimes what the manufacturers do, uh, they get the materials for cheaper prices, and they do it. But they basically don't understand what are the consequences of, operating something which is not suitable for usage for that kind of application. So that is frequently observed, right, at least in India. Apart from that, some of the cases that were registered are due to you know uh, high temperature stresses that are mechanically applied on the walls of the tubes of economizers or boilers or superheaters. So apart from the mechanical stresses, mostly what I observed was due to dissimilar material welding, because the material properties, they never match.
Okay.
Yeah.
Okay. Thank you.
Thank you.
So, okay. So let's stop sharing.